a little bit about just what it is. So for some folks on the call, that might be a little bit of a review or something you're already aware of, but then I'll share some new work as well. So just at the onset, I want to acknowledge a whole host of folks who have contributed to the ACPF over time, and also some funding sources as well. So particularly want to highlight USDA ARS folks, Mark Tomer, Dave James, Sarah Porter, and Jess Van Horn, all who are no longer actually at the ARS, but still continue to be really wonderful and valuable collaborators. Folks at Iowa State, namely led by Rick Cruz at the Iowa Water Center and Robin McNeely at the ISU GIS facility. University of Wisconsin-Madison, Rebecca Power and Ann Nardi's team, University of Minnesota, Ann Lewandowski's team, and then Linda Prokopi's team at Purdue, as well as a number of other really wonderful supporters who are using the ACPF and providing really good feedback. And then in terms of support, ARS, NRCS, and US EPA, as well as NRCS collaborators. So today, I really want to talk a little bit about conservation planning, and importantly, sort of how technology is this opportunity for conservation planning, both in terms of geospatial data and in terms of tools. And then I'll talk a little bit about what the ACPF is and how it works. I'll share a little bit about where it might be most applicable and who's using it. And then recent developments, namely in terms of nitrate reduction and accounting for financial costs. And then I'll talk a little bit about future directives, which gets at some of the benefits and then expanding applications of ACPF in conservation planning. So I know most folks on this call are really well acquainted with the Corn Belt system and sort of our current scenario or our current situation, but I want to talk a little bit about it just to sort of set up why we arrive at conservation planning and technology as a key step forward. So most of us anyways, work in the US Corn Belt, and we know that some of the leading crops here include things like corn grain, soybeans, ethanol, eggs, and hogs. And in fact, that states like Iowa and Illinois consistently lead the nation in the production of these commodities. And that's really positive, right? That's important to our cultural values, our economic systems. But there are negative externalities associated with the production of those agricultural commodities, namely row crop corn and soybeans. So when we think about nitrogen, we know that in systems where we have relatively low release, relatively fertile soils, and then we grow corn and beans, we can have nitrate leaching through namely subsurface tile drainage. So that tile drainage is important to dry out the soil and allow us to produce crops, but nitrate leaves in those tile drains and often ends up in our surface waters. On the phosphorus side, we know that most of the phosphorus in our agricultural landscapes is going to leave via runoff and erosion, which you can see in that diagram on the left. Again, an externality that we're concerned about as it relates to surface water quality. So as I mentioned, nitrogen and phosphorus leaving our agricultural systems are concerning, and they're concerning both at regional and local levels, right? So when we look at this graph in the center of the slide, what this is showing is the square kilometers of the Gulf hypoxic zone. And what you can see is that in the previous 5 years, in 2017, we actually saw the largest hypoxic zone. So really continuing to be challenged regionally by excess nutrients. And then locally, we know that there are impacts too, right? So local eutrophication, local algal blooms, those present challenges both in terms of drinking water quality and in terms of recreational opportunities. And so to start to address these issues, the Gulf Hypoxia Task Force was formed and really helped to usher in a series of nutrient management strategies at the state level across the Mississippi River Basin. And then one of the primary ways of reducing nutrients in those nutrient reduction strategies is conservation practices. And so over the past 25 or so odd years, we've invested a lot of resources and a lot of money in conservation practice implementation in our state and across the larger Corn Belt. So what this graph shows is just the state of Iowa and its conservation payments. So as we move from 1995 toward 2019, we're seeing payments anywhere from approximately $150 million up to $400 million. So over the past 25 years, about $6.2 billion of conservation payment investment here in Iowa. And this has led to real practices on our landscape, right? We're aware that programs like conservation reserve, environmental quality incentives, conservation stewardship, there are 110-ish thousand active contracts covering about 3.2 million acres. And they're putting practices on the landscape like land retirement, cover crops, riparian and saturated buffers that have an effect on reducing nitrogen and phosphorus loss in our landscape. Yet, really identifying the key places that might be most relevant to place these practices in our landscape to really boost those environmental benefits, that's still something that we're figuring out. And that's really where the role of technology can play a key part. And that's not exactly new either, right? So this paper was published in the early 2000s. There are other papers by Jorge Delgado and Craig Cox that get at something similar, which is that precision conservation, or what we might call spatially targeted conservation, really offers that opportunity to use spatial technology to identify those parts of the landscape that might be prone to nitrogen and phosphorus loss, and to see what kinds of best management practices might be most relevant to place in those parts of the landscape. So precision conservation or spatially targeted conservation using GPS, remote sensing, and GIS to really understand what the surface of our fields look like and where opportunities might lie. And so pragmatically or practically speaking, the kinds of data that we might use to harness a spatially targeted or a precision conservation approach might include things like elevation, which is represented in that hillshade diagram on the left-hand side of the slide, hydrology represented by watersheds, land management and land use, and then soils. And really importantly, in the last 15 or so years, these kind of geospatial data have become increasingly publicly available at finer and finer resolutions. So really harnessing data in a new way. And that sort of leads me to the ACPF, which is really a tool to help us understand where we might see resource concerns, how to address those resource concerns, and does so by harnessing that geospatial data and those tools. So the Agricultural Conservation Planning Framework, or the ACPF, is at its core a science-based, data-driven approach to understanding agricultural conservation planning at small watershed. So think about like Huck 12 scale, as well as field scale. The tool identifies these opportunities to place best management practices that address those resource concerns. And I think one of the really important parts about the tool is that it's able to sort of, the tool itself and the theoretical framework around the tool recognizes that farms and watersheds are really heterogeneous. And that means in terms of their soils and their land use and their hydrology and their management. So getting at sort of both of those aspects, and that relates to identifying localized areas of resource concern. So we need to understand that really fine resolution information. And then it cites suitable practices in field, at edge of field, and in downstream locations. And I think the other important part about ACPF is that it's non-prescriptive, right? So it offers producers or stakeholders a menu of conservation options that are tailored to resource concerns and their specific geographic location. But it's really about starting a conversation between a landowner and then a conservation planner. So it's a really unique opportunity. All right, so how does it actually work? So the Agricultural Conservation Planning Framework is based off of, it has 3 components. So first of all, it's based off of a conceptual framework, which you can see on the right-hand side of this slide, that's really grounded in foundations of agricultural watershed management. There's publicly available geospatial data sets related to things like elevation, soils, and land use. And then the theoretical framework and the data are operationalized in a series of GIS-based tools that identify those key opportunity locations. So I want to just take a minute to step through that figure on the right-hand side of the slide. There's a lot going on there, but I want to highlight sort of some key pieces of it that get at the approach of the ACPF. So if you look at the top of that figure, that sort of orange or brownish colored box at the very top, ideally, right, we'd have practices like appropriate nutrient management, so getting at 4 Rs, reduced tillage, to really avoid and control issues related to nutrient loss right at the start. But we also know that in a lot of places, that's not enough. That's not going to help us achieve those nutrient reduction goals enough. So that brings us to sort of the center of the diagram. And if you look at the column on the far left, that column relates to scale. So the scale at which we would control, trap, and treat nutrients in fields, below fields, and in our riparian zones. And then those two columns on the right and in the center, those get at those different nutrients, right? So nitrate leaving via tile drain in the center, and then surface runoff and phosphorus on the far right side. And then those sort of cells in the interior of that matrix, those identify potential practices that might address that nutrient or resource concern at that scale. And this is really the framework that the ACPF uses in terms of thinking about conservation practice siting, suitable locations for practices. All right, so what about the publicly available geospatial data? So the ACPF currently has databases downloadable for 11 states across the US Corn Belt. So you can see those highlighted in those colored watersheds in the map on the upper right. And those that geographic extent sort of continues to grow, which is really exciting. So if you go to the ACPF website and you want to download a Huck 12 watershed database, what would you get? So first you get a 6-year land use and crop history table. You get soils data, field boundaries, and watershed Huck 12 watershed boundaries. You can see the sources of those data in the table on the lower right. You'd also need to identify a digital elevation map, and that would have to be from the user. So you'd have to basically find that yourself. So I'm going to sort of step through some of these key data layers just to give us an idea of what's in the data that you download. So if we start with land use information. So land use information in the ACPF comes from the USDA National Agricultural Statistics Service Cropscape cropland data layer, which is that image on the left-hand side of the slide. Basically, the USDA uses satellites and surveys to identify major commodity crops that are grown on an annual basis, and then makes those publicly available. ACPF uses those data to inform its land use. So as we move from the cropland data layer to the right side of the slide, basically what you're seeing is a summary of that information at the field level. So we're also incorporating field boundaries here. So you can see from this watershed on the right that there's a lot of corn and soybeans. And that's the crop rotation. So the ACPF is including 6 years of data to get at that crop rotation. And you can see that represented in that very small table in the upper right, which gets at sort of how many years of corn, beans, or other crops are grown, and what's the general crop rotation or general land use we'd assign to each field. The second data layer I want to highlight is soils. So the soils layer in the ACPF is from the USDA National Soil Survey GSIRGO database. So in addition to the 10-meter raster that you would download, that you would get as part of the ACPF download, you also get a subset of curated tables related to soil horizon, soil texture, and parent material. And those soil properties are used during the processing phase to, again, think about where those resource concerns might be and where practices might be cited. And then the final layer, and I'd argue potentially the most important piece of data, is the digital elevation model. And again, this isn't part of the download that you would get from the ACPF. You would have to identify that somewhere else. So in Iowa, you could download it from a number of different sources at the 2-meter resolution. So the elevation is particularly important, but in addition to elevation, the digital elevation model allows us to understand the slope that we might encounter in any given field, as well as to start understanding where water flows on the landscape, which is really the key piece of a lot of this. And so using the elevation information, the digital elevation model, we can look at flow accumulation and flow direction, which you see in that map on the far right. And again, the elevation piece is really critical, right? Because it allows us to identify where those critical flow paths might be, and then where conservation practices might be best cited to address those. So the final component of the ACPF is a GIS-based toolbox that cites, that processes the input information and then cites conservation practices or identifies opportunities for conservation practices. So we take those input layers that I just shared about, so watershed boundary, field boundaries, soils, land use, and elevation. And then there are 6 key processes that the tool completes. So the tool goes through a DEM sort of preparation process, develops stream networks and catchments, categorizes fields. So this is really the step where we might identify where we might be seeing nitrate loss through tile drainage, and also where runoff might be a challenge. And then those last 3 steps are related to citing best management practices or looking for opportunities to cite those practices in the landscape. There's a screenshot of the actual tool itself and the steps that would be involved in each of those key processes on the far right-hand side of the slide. And ultimately, the output from the ACPF are watershed and field level land use scenarios, so integrating those conservation practices and data that are associated with those conservation practices. So in terms of conservation practices that ACPF currently has in its wheelhouse, there are 9 what I would call targeted practices. So those would be practices that are targeted to a specific spot on the landscape based on their conservation practice standards. Those would include things like grassed waterways, contour buffer strips, bioreactors, wetlands, wascobs, and buffers. In addition, the user can consider other practices that are less targeted. So those would be like cover crops or tillage. Those aren't directly included in the suite of conservation practices in the tool. The tool also includes farm ponds, which I don't have up here. So when we think about outputs itself, so the ACPF results can really inform a number of different steps in conservation planning. So first of all, the ACPF can help to inform identification of problems and really opportunities that are on the landscape. So for example, in this watershed map on the right-hand side of the slide, you can see that we've identified tile drainage and runoff risk by field. So that might be a really important spot to start thinking about. Maybe there might be some challenges that we'd like to address. We'd like to get out to the field and look at sort of what's going on. The ACPF's data can also help with inventorying and analyzing resources. So remember, as part of the ACPF, there's soils, elevation, land use. All of that information can inform our understanding of current resources. And then finally, sort of the core, right, formulating and evaluating alternatives, which is what you'll see on this map in terms of bioreactors, contour buffer strips, and nutrient removal wetlands. So in this particular scenario, we're citing those 3 practices, and you can see those in that cutout in the upper right, where individual fields have bioreactors in green boxes, nutrient removal wetlands in purple, and then contour buffer strips in that orange, with that orange line. So when we think about where the ACPF is applicable, right, I already mentioned that it's the data set and the tool are available for 11 states across the Corn Belt, and that continues to expand. When we actually think about using the tool itself, though, the tool really is operationalized at that Huck 12 scale, so that small watershed scale. That's deliberate, right? A lot of management decisions get made at that Huck 12 scale. A lot of watershed projects really occur at that Huck 12 scale. And then in addition to that watershed scale, the tool also allows us to zoom down to the field scale. So we can start to think about outcomes not only in terms of the watershed, but also more locally to individual fields, and really provide options for landowners and watershed stakeholders. So who can the ACPF be used by? So the ACPF has been available, I'd say, pretty widely, probably the last 5 to 7 years. That might be optimistic. And over that time period, we've seen a number of different users. So both public and private users, and a number of partnership users, I'd say. So those include folks like conservation planners and resource managers across a whole host of government agencies, industry, and nonprofits. And those organizations primarily they run the tool, They evaluate the data and they present that information to landowners and farmers and watershed organizations and other stakeholder groups. So the tool itself, I will say, requires some GIS skills to actually run. So researchers, scientists, and planners can run the tool with a lot of input from landowners and farmers. So it's again a really nice tool to interface between the end stakeholder and sort of folks who are doing resource management. There's been, this is not an exhaustive list on the bottom of this slide, but there's been a number of social science studies that have evaluated the ACPF in the context of conservation planners using it, and then end users, so farmers using it as well. So that's, I think, another strong piece of ACPF. Yeah. All right, so I want to chat a little bit about some of the recent developments of the ACPF. And in particular, I want to highlight some work that is really recent by a master's student who just finished in natural resource ecology and management at Iowa State, Emma Brevard, who worked with John Tyndall, myself, and Dave James on the ACPF financial and nutrient reduction toolbox, which we're calling ACPF Fine Art. I'm going to highlight some of her work. So conservation practice programming and implementation, we know, is potentially really expensive, right? So several of the scenarios in the nutrient reduction strategy that look at conservation implementation to reach those reduction goals, we're talking about over $1 billion on an annual basis. That's a really pricey measure, right? Especially when we consider over the past 25 years, we've invested a total of $6.2 billion. So it's a lot of money. Newly and publicly available data and tools like the ACPF can help us to identify more strategic locations on the landscape. And in addition to the biophysical data, we now have a lot of economic data. So can we start to integrate that economic data to really allow for better decision-making in conservation planning and practice placement? And so Emma's work really was on the development of multi-state ACPF compatible economic data sets, toolboxes, and outputs to allow users of the ACPF to do that, to really be able to harness that decision-making power. And so I'm going to talk first about the cost side of things. So the cost of conservation practices, when we think about those, we really separate them into two categories: direct costs and opportunity costs. Direct costs are the kind of costs we think about from actually implementing the practice. So that would be things like preparing a site to put in a buffer, establishing and installing maybe plants or any equipment that we might have, materials, labor, basic management over time. Those would be direct costs. And then those costs are annualized over a time horizon, in this case, 20 years at a 2% discount rate, and then applied on a BMP scale unit, so per area of BMP. And what this means is per treated area. So for example, 1 acre or hectare of a contour buffer would treat 9 crop acres or hectares. And so when Emma put together this data, you can see the results of that on the right-hand side of the slide. So when we think about the average direct cost in 2020 dollars of conservation per unit per year, quite a bit of variability, right? So when we think about something like a wetland, we're talking about somewhere close to $4,000 per hectare in direct costs versus something like a contour buffer strip where we might be closer to $90 per hectare. These costs are going to vary a lot depending on the site. So this is sort of a broad brushstroke, but it does give us an idea of the variability in cost when we start to think about some of these practices and the acres they treat. So the second part of the costs are opportunity costs. And opportunity costs exist when we're going to take land out of production to put in a practice. So for example, that nutrient removal wetland, we would take an area of cropped acres out of production. And in addition to the direct costs we just talked about, there'd also be foregone income associated with removing that land from cultivation. So to account for that foregone income, we use an area-weighted county land rent proxy. and the G-Circle soil productivity indices. So that's a mouthful. So I'm going to sort of use an example to help with explaining this. So in the image on the lower left-hand side of the slide, you can see a hypothetical 10-acre wetland. And that wetland has different soil map units underneath that hypothetical wetland. And those soils have different productivity indices associated with them. In Iowa, we use the corn suitability rating. At the national level, it's the NCCPI. Other states have individual productivity indices. Basically, all these are getting at is how good is this soil at growing crops. And in Iowa, it turns out the closer you get to 100, the better those soils are at growing crops. So when we look back at this wetland, you can see a bit of variability in terms of productivity, right? So everything from 42, not so great, up to 89, getting better. So to understand the foregone costs from putting this area into a wetland, we calculate an area-weighted corn suitability rating. So for this particular example, that would be 77. We then use the published rental rates from the Ag Decision Maker. So that's work led by Alejandro Plastina. Those are published on an annual basis at the county level. So that gives us an idea of, in this county, in 2020, what's the average land rent? And then there's also an average CSR point. So what that allows us to do is to say, for each CSR point, what's the dollar amount? So we can correlate CSR and dollars. So in this case, if we have this area weighted average of 77 and we look at the per CSR point land rental rate, that gives us about $209 per acre in this case. So scaled to 10 acres, we're looking at about $2,000 per year in added land rent, so added opportunity costs. So for a wetland in this case, that's plus that $4,000 per year per hectare from that direct cost. So Emma aggregated all of those data, so about direct costs and opportunity costs. And then the next step after the data are developed is to really get into how to make it compatible with ACPF in GIS and to build those tools and a toolbox. So the ACPF Financial Toolbox has two tools, which you can see in the diagram on the left-hand side of the screenshot on the left-hand side of the screen. And those two tools do two really important things. So first of all, the first tool calculates expected nitrogen requirements based on crop rotation at the field level using maximum return to nitrogen. So if you look at the screenshot in the center of your screen, you'll see that to do that, we need infield boundaries and that land use table. And then those default fertilizer values that you see in that screenshot, those are from the maximum return to nitrogen calculations. They can be changed by the user if you have other information about the watershed or the field you're working in. And so what this basically, the output from this tool is an understanding of the nitrogen requirements over that 6-year crop rotation in any field in the watershed. And then the tool actually takes that a step further and says, okay, based on those nitrogen requirements, using information related to soils and geographic location, how much of that nitrogen is likely available for leaching? And that's the fraction of nitrogen that our best management practices are actually going to work on, basically. So that's the output, and we call that the FERT table or the fertilizer table that comes out of this tool. So armed with that information, we go to the next tool in the toolbox, which looks at the cost and the load reduction. So the key inputs for that second tool include the field boundaries, that land use table, the nutrient or the fertilizer table from the previous step, and then soils information, as well as flow information, so flow direction and flow accumulation. And those conservation practice layers that you created in the previous part of the ACPF. So for example, the layer of grassed waterways or the layer of contour buffer strips. The user can actually choose to only have certain contour buffer strips be analyzed. So you can go down to the individual practice and really pull out the practices that you want evaluated, or you can put the whole layer in. And the output from this second tool are a number of attribute tables that show a whole host of information related to outcomes from the conservation scenario. So that includes which conservation practices, which fields they're in, opportunity acres and costs, direct costs, the treated area, the nitrogen load and load reduction potential from implementing those practices. And that reduction potential, that comes from the Iowa nutrient reduction strategy. So it's, for example, for cover crops, it'd be somewhere around 30%. And then load reduction at both the field and watershed levels, total costs, and then that cost efficiency piece of cost per pound of N reduced. So all of this information is available for the end user. And so if we look at just an example of sort of this in action in Big Creek Watershed, which is located on the Des Moines Lobe in central Iowa, what you're looking at is sort of the upper watershed, which is 2 Huck 12s. What you can see is that the watershed is something like 90 to 95% corn and soybeans. So a lot of corn and soybeans here. And those two watersheds drain into Big Creek Lake, which has had some challenges regarding nutrient reduction. So if we run the ACPF and we have a conservation scenario where we have bioreactors, cover crops, and nutrient removal wetlands, so that map on the left-hand side of the screen, there are a number of details that we can glean just from the ACPF. So that would be the number of practices, the area removed from cultivation. But those next 4 rows really get at the addition of the ACPF fine art, which is how many acres are treated, what's the total cost, how many kilograms, and what's the percentage of the amount of nitrate reduced, and what's the average cost effectiveness. And I think there's a whole host of potentially useful information here, right? So the scenario as a whole has useful information about achieving nutrient reduction. For example, this scenario is about 59%. But then you can also see the variability in terms of different conservation practices. So when we look at, for example, bioreactors, pretty good deal, about $1 a kilogram of N reduced. Other practices, so for example, cover crops, we're looking at about $19.20 per kilogram. So there's some really important differences and nuances in the cost effectiveness of these different practices. You can also see variability in terms of nitrate reduction. So cover crops are really pulling their weight, right? We're talking about a 30-ish, 31% reduction in this particular scenario. So again, a lot of cost and outcome information available using ACPF fine art. You can also use it to look at how to best maximize potential resources. So for example, based on that scenario I showed with all potential practices, so bioreactors, cover crops, and wetlands, you can see that in the second row of this table. But if we're in that scenario, we're achieving a 59% nitrogen reduction. We're really looking for 41% though, right? So if we prioritize based on different attributes, so whether practices target the highest end load, whether individual practices have the lowest cost, or whether individual practices are most cost effective, that really impacts our total cost. So basically, if we prioritize individual practices, we can have a variation in total cost of about $1 million when we talk about achieving the same nutrient reduction outcome. It also impacts cost effectiveness and the number of best management practices that have to be installed in that would need to be installed in the watershed. So for example, if we target high load, we're looking at about $2.3 million a year and about 310 best management practices in that watershed. If we target cost effectiveness, we're shaving off about $400,000, but we're going to have to put in 200 more best management practices. So it really, I think, highlights the need to talk about these pragmatic trade-offs and synergies when we think about actually putting conservation on the landscape. So I want to sort of wrap up I should say one more thing about that tool. So Emma Brevard has submitted her paper that's focused on this tool, and we're currently working to make the toolbox and the data available publicly, and that'll be probably where other ACPF data and tools are located. So that will be made publicly available in the near term, I'd say. And right now it's really focused on Iowa, but we have started branching out and looking at Minnesota and Illinois as well. So the last thing I sort of want to leave folks with before hopefully we have time for questions is just sort of future directions of ACPF. And I actually had a really hard time with this slide because I think there's a lot of cool things to do yet. So this is a laundry list. I apologize, there's a lot of text on this slide, but this is me sort of being excited about a lot of opportunities. So if you think a little bit about what we just talked about, right? An obvious question in Iowa's landscape is like, great, we know about nitrogen, but what about phosphorus? So that's certainly on our radar. We have a master's student, Chelsea Ferry, who's working a little bit on thinking about phosphorus and sediment and how we might integrate those into the ACPF fine art. And then we're also interested in thinking more about direct costs and opportunity costs across larger geographic landscapes. So integrating more states and really thinking about what are the roles of different ways of thinking about opportunity costs. So we're using productivity indices tied to soil, but is that a good approach to that? Are there better approaches to assessing productivity and thus land rent that we could be looking at? We're interested in quantifying other ecosystem service outcomes and their values. So you'll remember that I said cover crops were one of the more expensive per kilogram and reduced practices. We're not accounting for any of the in-field benefits that cover crops might have. So how do we do that in a pragmatic way for stakeholders? And then related to that, are there ways that we could tie in potential incentives? So conservation program dollars or markets. So carbon's really hot, right? So what does the cost look like for a producer who's interested in participating in a program or a market versus someone who might not want to do that? The ACPF has been developed in the Corn Belt, so the practices and some of the DEMs and stream characterization are really tailored to the Corn Belt. So exploring how to make it applicable across broader geographic scales is certainly an important step. Thanks to some funding from INRC, we're looking at policy work. So what are different policy scenarios and how can we use ACPF fine art to evaluate those? Are there opportunities to integrate ACPF with other tools? So for example, WEP and DEP, so the Daily Erosion Project over at the Iowa Water Center with Rick Cruz's group. What about SWOT? So there's just a paper that came out from Minnesota maybe last week that looked at ACPF plus SWOT and really thinking about how those could jive. And then finally, just increasing the accessibility and applicability of the ACPF. So we're just coming out of a 2-year agreement with NRCS and about to start another 3-year agreement to really start to evaluate opportunities, again, to integrate ACPF in the conservation planning process with NRCS partners and potentially NRCS themselves. And then exploring really effective web-based services and apps to enhance applicability of ACPF. And so with that, I'll maybe end with just my contact information and the ACPF's website, which includes the database and tool downloads. Those are public. There's really nice examples of ACPF's application. ACPF has a number of peer-reviewed publications at this point that span sort of the technical to the outreach aspect of it. So probably nearing 25, if not more, publications about ACPF at this point. And then I want to highlight, if anyone on the call is really interested in ACPF, there's self-paced training that's available online. And then there's also cohort-based training. So that would have sort of a synchronous component. And if the cohort-based training is of interest, please feel free to send me an email and I can connect you to the people who are doing that. So with that, I guess I'll stop. And if there are questions, I'd be happy to try to answer those. Otherwise, thanks everybody for joining.
Anybody in the room? My question was when the tools were going to become available. But you answered that. Yeah, the support training. Yeah, nobody can hear me. Type in questions or unmute themselves.
Okay, so says to feel welcome to type in questions in the chat or unmute yourself and ask questions.
Just a second.
Mm.
If you want to pull up, okay. No.
Yeah, sure. Yeah, exactly. That's a great question, Anne. So I think so the fine art piece, the economic piece, so that those data sets about. No, that's okay. Yes. So Anna's asking about clarifying what is currently and maybe will be available online. So currently you can access ACPF's database and tools talked about. But the piece that's not available yet is the economic work from Emma Brevard. And that the data, so direct costs and opportunity costs for Iowa, will be available soon. And the tool, the toolbox and those two tools, those would also be publicly available soon. So folks could imagine downloading those just like they would the ACPF data and the ACPF toolbox, or in a similar way, probably. All right. Okay, so a question. Oh, Robin can't hear.
I'll assume.
Okay, so Harrison, so the cumulative scenario, assume that BMPs treat different soils and do not overlap. Okay, so a couple of that's a really good question. So first, that cumulative scenario that you saw, those BMPs are treating different soils potentially with different productivity indices and likely different nutrient potential nutrient challenges. So that's true. The part that I think is important to understand right now is sort of how we account for nutrient reduction. So in a field when there are, and I don't know if this is what you're getting at, Harrison, but I want to share about this. In a field where or in a catchment where there might be multiple practices, what's happening is that we're multiplying those practices to get a field or a catchment reduction. And then it's an additive effect to total at the watershed level. And that process is based on a paper by Lazarus, who's from Minnesota. And so that's sort of how that process works. So we're assuming that we wouldn't place a bioreactor on top of a wetland itself, but they may have a treated area that would overlap, I guess is the point there. That's a great question. Right. Yeah. So Matt just asked about if you had a field that had a cover crop applied, and then that field drained into a separate field, Matt, where a wetland occurred? Drained into a wetland. So right now it gets a little bit sticky because the way that the math is set up is that it's practices that occur in the same catchment area or the same field where we'd expect first that multiplicative effect across. So we'd multiply those nutrient reduction efficiencies together. And then all of the fields would be added basically to get the watershed level reduction. We don't know if there's anyone doing field work right now who studies the effective stacked practices. I would love to talk to you. So please reach out to me. I'd be thrilled to chat with you, particularly around nitrogen, but also for phosphorus. Anne. Yeah, so Anne just asked where the where we're at with the phosphorus. And I would say we're at the very start. We've had some conversations to try to identify sort of the best step forward for phosphorus. Phosphorus is a little more complicated than nitrogen because it behaves differently at different points in the landscape. So there's a difference between sheet and rill erosion, and then understanding sort of classic gully formation, and then even further on stream processes. And so we're hopeful to work with the Daily Erosion Project to get at some of the sheet and rill erosion. And then we've actually had a good conversation with Antonio Arenas about maybe integrating in some of his experiences to really get a picture of where phosphorus is moving and where it's being deposited. That's the other piece of it on the landscape. But that one's probably not in the immediate release category. I'd say we're looking at months or years for that probably. Adam Schneiders, if you have a question, please feel welcome to put it in the chat or ask. Matt mentioned that it looks like you have your hand raised.
I do. Matt always gives me grief for following these procedures too closely by raising my hand. I have two quick questions for you. One was related, and this is great development on this, by the way. I think it's really neat to see the different policy scenarios that you can put together. One question I had was related to a saturation analysis. When you look at what's already put in a watershed, do you see, I know we've done some of this like back of the napkin saturation to see what practices are possible versus what's actually there. Do you see opportunities for that being dialed in, more automated? I have a second question if there's time.
Yeah, Adam, that's a great question. So I'm going to start with the second piece of that, I think, because I heard that piece really clearly. So that's a great point about saturation and about thinking where practices currently are. We definitely, I think there's clear opportunities there. I neglected to put that on that last slide about sort of where those opportunities lie. I think we're in a pretty good spot to start doing that with the structural practices. So with the Iowa BMP mapping project, I think some of the other in-field practices, so fertilizer and manure application, cover crops, tillage, residue management, those I think that might there's good data that are coming about those, but I think that process might be a little longer. And I think there is a really good opportunity to start automating and saying, okay, what's there, what's not there, and potentially, what does that leave us with in terms of the wedge of addressing nutrient concerns in a particular watershed? And Adam, did you have a first part of that question that I may have missed?
It was, I switched from my headset, so hopefully you can hear me better. I had a first part was that I had a second question, so that's a good segue. The one other question I had, we're doing a lot of work using the nutrient tracking tool with cities that are making investments in a watershed. And it sounds like the ACPF can be integrated with other models. We were looking into that. I know as we get more cities making these investments to get credited for those nutrient reductions, do you see ACPF in the nutrient tracking tool being integrated in some way or seeing possibilities there?
Yeah, that's a great question. So again, I think there's a lot of possibility there. I have to be kind of candid here that I haven't done a lot of work with NTT. So, I think that's something we'd like to explore, just like, exploring things like SWOT or work with DEP. One thing I want to emphasize is that I think the ACPF is a really useful tool for thinking about in a given field or in a subcatchment of a watershed, really, what are those key opportunities? And I think, one caveat of using the ACPF is that it's not an engineering tool. So that would be something I think that we'd really want to explore in terms of application for some of those, those certification or those market components. Not that I don't think the possibilities there, but just that it would involve some really thoughtful discussions, I guess.
Thank you.
That's a great question. And actually, yes. So oh, sorry. Thanks, Matt. So Anne just asked if extended rotations would be included in the ACPF. And so we use that 6-year land use history. So we would be able to pick up on some of those extended rotations. And this is a little bit of a tangent here, but in the updated nutrient reduction efficiencies, which Matt and Tom and Chelsea Ferry and I are working on, we've split out 3- and 4-year reductions. And so we'll be able to really pick up on some of those nuances in that 6-year crop rotation as we go forward. Yeah, great question. Yeah. Other questions that folks might have? Yes, I'm going to step off of the screen.
Okay, I'll make a couple announcements. Thanks, Emily, for a great presentation. We will have this archived. Yes, yeah. Virtual round of applause. I was getting to that. So for everybody online, virtual round of applause. Thank you all for bearing with us today. We'll get it so that the second microphone works a little better in here next time. The most important one, I think, worked. It seemed like nobody typed in. They couldn't hear Emily as we went along. So I think that's what was most important. So thank you. Thanks, everybody, for attending. I just wanted, most of you probably got an email from Malcolm this week or yesterday, but September 17th, that afternoon, we're planning a tour of some water quality projects around Ames, going up to a wetland with Bill Crumpton, drainage water recycling site, and Bear Creek. So contact Malcolm if you want to attend. This is kind of a follow-on from what we did 2 years ago. And for those that are so inclined afterwards, maybe we can have a little optional social hour to do a little networking. But with that, we are close to 4 o'clock. So thanks, everybody, for attending, and thanks most to Emily for participating. Everybody have a great rest of the afternoon.